série de palestras de divulgação nesse colóquio, nós agora vamos ter o professor Khashayar Pakdaman, que ele é da Universidade de Paris 7 e, de fato, ele é formado originalmente pela École Polytechnique em Paris, e ele foi especializado inicialmente em engenharia. E ele é um engenheiro elétrico que, finalmente, o interesse dele por essa parte de biomatemática foi despertado num estágio que ele fez em Berkeley durante um ano, e a partir daí ele se moveu da parte para essa dinâmica de sistemas que, na verdade, são chamados redes neurais, e ele está interessado nisso desde... mas isso aí aconteceu em torno de uns 12 anos atrás. E ele também teve depois do estágio em Berkeley, ele passou 3 anos no Japão, numa faculdade lá de medicina, na verdade, e depois, finalmente, radicou-se na França, que está em Paris 7, e no Departamento de Biologia e Ciência da Computação. E ele continua até hoje, mas atualmente com interesse todo voltado em biomatemática. E hoje ele vai falar sobre código neurais. Tá? Então, por favor.
Thank you. So I would like to thank the organizers for inviting me to give this talk here. And I'm going to talk about the neurons, and I'm going to show a lot of experimental data. I would like to first make sure that you can all hear me. It's fine? Yes? Okay. And I guess you can all see me? Yes? And I think you can all also read this one. No problem. Yes? How about this one? Okay. This is more of a problem. So what we are trying to do is even more complicated than this, decoding this text. We are trying to decode the brain. So imagine that my first question would have been, can you read my brain? Can you read what is going on in my head? So when we are talking about neuronal coding, our goal is to understand what is going on in the brain and to be able to read what is going on in the mind when we are thinking, when we are planning some task. So this is our purpose. And I'm going to tell you a long story starting from 1920s until now about what have been done on this. But I can tell you first the conclusion. Usually we start with the introduction, but the conclusion would be that at the end I will show you some examples where we are able to read the brain. It means that we are able to see what is being planned directly from the brain without looking at the action. So this will be the final conclusion to which I will be reaching. So before that, I have to go through some introduction to biology. So I will leave this here so that you see throughout the presentation where we are. So I have to go through some biology very quickly and then show you some traditional analysis and then the final conclusions. So very quickly, the anatomy. So the nervous system is some kind of wiring through our body, and it allows us to sense our environment. This is the sensory system, and also to act on it. This is the motor system. So this is one representation of this wiring. And this is the peripheral nervous system, and this is the central one. This is the brain where the main part of the processing is going on. So our purpose is to understand this and how it's working. So the brain is composed of many units, and these units are called the neurons, and they come in different shapes. So you can see here there are neurons of different types. And they work in a very simple way. A neuron is an electrical device. So it's working very simply. If you put some electrical signal on it, if the signal is weak, we don't get any response. If the signal is strong enough, we get a response which is just an electric pulse. Okay, so it's very simple. We have input, and output is just an electric pulse. So this is called the dogma of neuronal coding, and it was discovered by Edgar Adrian. So this is what it says. It says that basically, imagine that we have a Morse code, In the Morse code, if I send SOS, it's dot, 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 dash, 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 dot, dot, dot. The dot and the dash do not change. Okay? It's always the same dot and dash. If I send another message, it's going to be dot and dash again. But it's going to be a different composition of dot and dash. So what matters here, we have a simpler code. We have only dots. So we get the signal and we get the dots. So what is going to matter to us is what is the relation between the signal that we put here and the dots that we are going to get outside. So this is understanding the neuronal code, is understanding the relation, how this is going to be encoded into the other. So this is the first rule that I think if you want to understand this talk, this is the one that you have to keep in mind throughout the presentation. This is what we want to understand, how to go from this one to this one. So actually, Adrian got the Nobel Prize for his discovery. He was the first one to state this. So let's see some example of this. How does it work? Here we have the input on this side. So here, this is the input. You see, it's very simple signal. It's being applied with different time. This is the neuron. The input is applied here, and we are monitoring what is going on. These are the pulses that are generated, and these are the dots that I have represented here. So what we are interested in is how this becomes this one. So you see that as we are increasing the duration, the number is increasing. So this is a schematic representation. Let's see some real data, what it looks like. This is one real recording from a single neuron. So this here, this lower part here, is the input, and the upper part is the recording from the neuron. This is this. So what we are going to do is try to see how this becomes this one. And in a simple way, we are going to count the number of dots in a window. And then we are going to slide this window throughout time. So we are going to apply the stimulation. The neuron is going to go something like this. Actually, when you do the experiments, you always listen to the neuron, because the ear is very good at picking up patterns. So the neuron is going tack, 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 something like this. And we are going to count the number of dots within a window. And this window is sliding throughout time. So what we are going to represent, this is called the firing rate of the neuron. So here you see the firing rate of the neuron against time. And in this experiment, there are 4 different experiments represented here, each one with a different stimulus amplitude. So we are increasing the amplitude. And what you see here is the firing rate stabilizes at a constant value, and this constant value depends on the input that we have applied. The neuron fires faster the higher the amplitude. So if I increase the amplitude, if the neuron is going, if I increase the amplitude, it goes something like this. This is a very simple relationship between the input and the output, and I can represent it in a schematic way. So on this side, I have 3 different inputs. On this side, I have the dots. And you see there are more dots for the larger amplitude than for the lower amplitude. I take this window, I count the number of dots. Here there is 4, here there is more, and so on. And I represent here the number of dots within that window against stimulus intensity. And I have a monotonic relation. And this monotonic relation is very good because if I know the stimulus intensity, then I get a single firing rate for it. And on the other hand, if I observe the rate, I can unambiguously derive the stimulus intensity. So this is a very simple code. Each stimulus intensity gets encoded into a single firing rate. And we think we are done. We have decoded the way the neurons are working. So with this, we can understand what is going on. We have a rate coding. So this was for a simple stimulation. So far, we are dealing with our way of working, which is to take a neuron, isolate it from its environment, and use a simple stimulation for it. Okay? This is like if I take the computer, I want to understand how it's working. I open it, I look at the components, I take the component out, and I analyze it irrespective, regardless of what is going on outside of this. This is what we are doing. And of course, after the constant stimulation, what we want to know is something a little bit more complicated. How about if we have a time-varying input, what is going to happen? So the first thing that we would expect is, can we just use the same relation that we had before with f monotonic and just replace the amplitude by something that depends on time? If this works, then we are completely done. We have everything about the neuron. But the experiments show that this doesn't work. We cannot just take the response to a stationary constant input and generalize it to what is varying in time. So we need to take some aspect of time into account. And the first method that was used for this is the linear system identification. So we are done with this first part, which was the introduction to neurosciences and the problem of rate coding. And we are going to see these aspects, which are more quantification of how the neuron works and where there's more interplay between the biological part and the mathematical part. So far, it was pretty easy to see that we had just a monotonic function. So what is linear system identification? This is what engineers used a lot. It's a black box approach. So the problem with biology is that there are no problems or hardly any problems that we can treat in biology starting from first principles. Even if I'm going to talk about neurons all the time, we don't know all of the details of the working of a neuron. This is not known. It's being still worked out. So we don't know the whole mechanisms, but we know the input and the output. We have a black box. And we want to understand the function that is going on from the observation of the input and the output. This is like I have the component from the computer. I can observe the input and the output, but I don't know exactly how it's working inside. So the basic method is just input-output. This is used in engineering, is to go to frequency domain and estimate some transfer function, which states the relation between the input and the output. So what this gives us is a transfer function in the frequency domain. So I have used the notation of engineers, which is that j squared is equal to -1. So this is, in the frequency domain, we have a transfer function. And in the time domain, we have a convolution. And this is the Fourier transform of this. They are related like that. Or if I put p here, this is Laplace transform of this quantity. So this is for a linear system. And for a linear system, if I know this function or this function, I know the response to any arbitrary input. So if I have characterized this, if I have estimated this, I know exactly what my system is going to do for any arbitrary input. And how do we do this? Let's do just one basic example how it works in the case of a simple equation. So I take a model for passive membrane. So this is RC circuit with C in parallel with R. Some current is injected here, and the output is the voltage applied here. So with these notations, I get this simple differential equation, and I can compute directly this function, which is the impulse response H. This one, this is the transfer function, and the output and the input, as I wrote before, are derived in the time domain as a convolution, and in the frequency domain as just the product of these two. So what we do with this is that we construct a Bode diagram. So I will be showing some Bode diagrams. I hope that you are familiar with this, or that this is reminding you some things that you have seen before. We take log of the modulus of this complex number, and this is called h in decibel. So we are representing h in decibel against log of the frequency, and we obtain this kind of shape. Now, this is speaking to me as a biologist. This is good for me because it's telling me what this neuron is doing. This neuron is operating as a low-pass filter. If I put inputs that have frequencies ranging here, they don't get distorted. They get through with some nice amplitude. But if I'm applying higher frequencies, they are being filtered out. So this is why this approach is very nice, because in the frequency domain, we can see the function that is being operated just by looking at the Bode diagram. So the people who did this in the first place, that was 50 years ago, more than 50 years ago. So I'm going to show a lot of original papers. I have Xeroxed the first pages of the paper so that you see them. So this is 1952, and it was done by Pringle and Wilson. And they were the first to apply this technique. So I remind you, the first one that I showed, Adrian, was in the 20s and 30s. So this is quite a few years later. And they thought that, OK, we can apply this technique to understand how the neurons work. And they applied it. And they applied it to a stretch receptor. So what is a stretch receptor? When I do this with my muscles, OK, or if you can do it, the stretch receptors are the receptors that are telling the brain this muscle is stretched, or now this one is stretched. They feel the stretch on the muscles, OK? And try this. Try to get air. Inspire. OK? Do it. You have to try it. Otherwise, it doesn't work. And you have to try it and go to the maximal level. Go. And you see it's blocked. You get blocked at some point. Because the stretch receptors are telling your brain, if you go further, you will break the bones here, something like that. So stretch receptors are pretty useful. If you touch the chair, okay, or if you touch a piece of wood, you feel the difference in texture. There are stretch receptors in the fingers, and they sense these mechanical stimuli. And these are what encodes our sense of texture and touch. So how they did this is that they want to understand how one of these is working. So they put it here. It's this tiny thing. It has a string attached to it. And the string goes to this device. And this part is oscillating. OK, this part is oscillating. This part is fixed. So it pulls on this and pulls like this. So this is how they devised some system to get a mechanical sinusoidal input applied to the stretch receptor. And then they get this output. So these are not the dots, but directly the firing rate. Okay? I did not represent the dots here. But this neuron is going like something like this. It's accelerating, slowing down, accelerating, slowing down. And with this output and this input, we can try to estimate directly from the data, this is what they did, some transfer function. And this is the result. I don't know if this is not the transfer function, but this is the impulse response. So this is in time domain. This is the data. You see some scatter because of the variability that we get in experiments. And this is what they estimated. And this is on the same one, but here the time is longer. This is 20 seconds. This is only 1.5. So this is just the beginning here. And the fit is very nice. And they estimated this function. The form of the function is not very important to us. It's just that they could do it. That matters. So this is 1952. We jump for a decade. And we see this one. I don't expect you to be able to read this one. The thing that matters is that the journal where this was published. So this is 1963, roughly 10 years after that one, and it's Nature. For biologists, there are 3 journals that matter a lot: Nature, Science, and Proceedings of the National Academy of Sciences of the USA. If something is published in one of these 3 journals, it gets a high impact, and it becomes mainstream. So what I'm showing you here is that a few years later, this approach became part of mainstream biology to do this kind of analysis to try to estimate the function based on system identification. And progressively in time, it became quite sophisticated. But before showing you the last example of this domain, let's just take the time to look at this in a little bit more formal way. So we have a system that is stabilized at an equilibrium point and it has some dynamics, and it's stabilized there. And we do some small perturbation of this. So roughly, this linear system identification is telling us that if this is small, then I take the derivative of f, and I approximate x by this y. So I have a linear system. It's a rough approximation, and it works only if this is small enough. And this is f prime is what we estimate, actually exponential of this a, for instance. Exponential of a of t will be our impulse response. So this is basically what we are doing. And of course, we should keep in mind that this holds only if y does not grow too much. So let's take the final example of this method. This is in 1975, so we jump another decade. And you see small signal analysis. So people are aware that to apply this technique, we have to keep it small. And this is small sinusoidal input. And it's applied, again, to stretch receptors of frog and cat. Lobster, frog, and cat. And what does it look like? What do the Bode diagrams look like? So the Bode diagram is this one. These dots are the experimental data. So here I have log of omega, and here I have the gain in decibel. The dots are the data, and these ones come from some theoretical estimate. So it seems that the fitting is very nice. No? If I ever have some kind of fit like this between my experimental data and my theory, I'm very happy. This looks very good. Or does it? Why this is not good? Because we have resonance here. So we said that these things work only if we are dealing with something that remains small in time. But this resonance is indicating that the response is getting higher and higher. Why this is not good? Why this shows that this approach is failing is just, we can take a simple example. It's just like, let's take the linear pendulum. If we take a linear pendulum and we put some periodic forcing here, what is going to happen is that there are regions in the parameter. So I have omega here, A here, so these are the two parameters. Omega is here and A is here. And there are regions of resonance. No matter how small A is, there are regions of resonance. Regions of resonance are regions in which X becomes unbounded as time goes forward. So we are moving out, if we have resonance, we are moving out of the validity of linearization. This is the problem that was apparent in that previous case where it seems that the fitting was so nice. So what we have to do is, okay, it's invalid. We have to take into account the nonlinearity. And for the pendulum, if we take into account the nonlinearity, suddenly we obtain many different things that we could not obtain just by analyzing the linearized system. And this is what happens to neurons also. So we are facing the problem that we have to extend our linear approach to something else. The first one is to deal with it like engineers did. So they are very tricky devices and methods that allow to extend the linear one, identification, to nonlinear systems. Another one is, okay, we observed that for periodic forcing. How about if we replace periodic forcing with white Gaussian noise? And this one also works for nonlinear systems. This is called Wiener chaos expansion. So I will not show much of this in this application. I will just say now a few words about how it works. So we have the Wiener integral, which is an isometry between L2 of 0, 1 and L2, which is the square integrable functions of 0, 1, and on the other hand, the square integrable functionals of the Brownian. So I have an isometry, so I can take an orthonormal basis of the first Hilbert space and just send it to the other one. So it means that if I have functionals of the Brownian, and the functionals of the Brownian for me are the outputs of the neuron in response to a white Gaussian noise, then I can decompose this into some kind of basis, orthonormal basis. This is an extension of Fourier analysis, because in Fourier analysis, in Fourier series, what do? We take something that we have, and we do its decomposition into a basis, into an orthonormal basis. So white Gaussian noise analysis is the same thing. We are doing the same thing, only we are using functionals instead of functions. So we can apply that technique here, and we can analyze nonlinear systems like that. And if you want another way to look at it, if we have a Volterra expansion, it's some kind of Schmidt orthonormalization of this Volterra expansion that we are doing. And we can estimate those things. And it's been done, and it's continuously done for over 30 years in neurosciences. But I will stress another method, which is to switch completely to a different framework and use dynamical systems to analyze this. And this was done actually before the paper of Chaplain, which was 75. This was done in 64, and you see the journal is Science. The other one was Nature, this is Science. So this is also this paper, and let's see what they did in this case. So what they did is schematically represented here. They had a two-neuron system. They take this input, they apply it to this first neuron, or this one to this one. So this is going to fire periodically. And then there's a second neuron which receives its input from this one. And what matters here is that first we have inhibition here. So this first neuron is slowing down this one. And this one is naturally a pacemaker neuron. A pacemaker neuron is something like the heart. It's beating naturally, periodically. Okay? So I have a pacemaker neuron, and I apply inhibition to it. And I increase the rate of inhibition by increasing the input. So if rate coding works, then the higher the input, the stronger the inhibition here, and the lower the firing rate of the neuron. But still, I get a one-to-one relationship between the input and the output. It's monotonic decreasing. So I can identify one with the other easily. So if rate coding should be working, things should be like that. And this is what the experiments look like. So the experiments clearly don't look like what we expect. We have a rough pattern like this, monotonic, it's decreasing, but we have segments of what is called paradoxical acceleration. Here, I'm increasing the input frequency and also the output frequency. I'm increasing inhibition, and the neuron is firing faster and faster. This is why it's called paradoxical segment. And how do we go for understanding this? Of course, first we look at the data. What is happening there? So if we look at those regions where we have these paradoxical segments, we see that for one input, for instance, we get 3 discharges. This is why the output firing rate is proportional to the input. Here we have for each input 3 firings. Here for each input 1 firing. So this means that the output rate is equal to the input rate. And here I have tried to represent the red dots are the input and the blue dots are the output. And here you can see every input is followed by 2 output. So we have this kind of relationship. So those segments show us that these patterns of periodic repetition actually occur over a range of frequencies, input frequencies. So this is what we are trying to understand. And how do we go about this? So to understand the procedure that was used, we have to try some kind of mental experiment, which is easy. Imagine that you go on camping with a friend and that you spend the day, it's very actively, and at night you go into a tent with your friend and you want to go to sleep. You are very tired, and you go to sleep, you close your eyes, and after a few minutes you hear. Of course, at first you try to accommodate, but after some time it becomes annoying. So what do? You push a little bit, okay? Your friend, you try to change his position. And what happens is that it stops. So you are happy, and then a few seconds later, it starts again. So this is exactly the key experiment. Let's try to see what is happening. We have the snoring that is going on like this. Okay? And at some point we do the perturbation. And then it resumes again. Okay? So if I had not done this perturbation, what would have happened? This one would have continued like this. So 2 key points appear from this simple experiment. One is that after the perturbation, we go back to the same period and amplitude as before. And the second one is that we have a phase shift. So we can do exactly this experiment with our pacemaker neuron and look at what is going to happen. This is schematically. So in our notations for biologists, n is natural period, is not some integer. So n stands for natural. So n is the natural period. We have the control. The control is here. We make the perturbation at some phase, and we get a phase shift here after some time. And what is important is that this phase shift here depends on the amplitude, of course, but also the phase of the stimulation. So we have some map that is going on from theta to phi, and theta is between 0, n, and phi is between 0, n, so we can say this is a circle map if n is equal to 1. So we have transformed our problem into a problem of a circle map. And if we are applying if we apply periodically the perturbation, this is I is the interval between two consecutive perturbations, n is the natural period, then we have theta 2, which is the phase of the second stimulation, which can be expressed as a function of the phase of the first stimulation, plus I. Of course, this disappears because of the modulo. So what we need to know is what is the relation between this and what we wanted to understand, which were the paradoxical segments. And this becomes very clear. So we are iterating this map. This is a circle map, so I've represented it here. And what we are changing is the value of I. If I'm accelerating, it means that I'm decreasing this value of this interval. So look, if I start from a position like this, I have this fixed point. This fixed point corresponds to 1, 1. One input, one output. One input, one output. So it's locked. And then I increase I, and this fixed point remains until this other value of I. So this is going to come down until this. So it explains me that for a range of I will have 1-to-1 phase locking. This explains me why for a range I have this paradoxical segment. For some range of I get this. So more generally, all the periodic orbits of this map will explain me the different paradoxical segments that I have. So far, there has been no mathematics until this point. This is what was done by biologists. All of this was done by biologists so far. There's no theorems involved. There's nothing. They just observed what we know about snoring or something, or locomotion or respiration, and they applied it to this neuron, and they realized that to understand it, we had to look at the periodic orbits of this map. So here, this is where the big change occurred, is the contribution of mathematics, because we are actually making a model. We start with some observations. The observation is that, okay, it oscillates periodically, and if I perturb it, it returns to it. Okay? These are the two. So we say that, okay, maybe this system is acting like a locally asymptotically stable limit cycle. We don't know what is the phase space. We don't know what are the equations governing this. We don't know anything. We just know that it's behaving like that. So we have only a geometric model with no reference to the equations or the mechanisms. We just feel that this is the same as that one. So what do we get is that if we have this kind of limit cycle, okay, we can take, so this is the limit cycle, an isolated periodic orbit, which is locally asymptotically stable. We can take a point arbitrarily and take it as the reference. This is exactly like we take the clock here, and we have a reference point here, which is on top of it. And then each point is unambiguously characterized by the time elapsed to go to here. This is exactly like the clock. Okay, so x of phi is unambiguously characterized. If I know phi, I know x. If I know x, I know phi. And I look at the time t map. Every n map, actually, time n map. And for that map, which is the flow taken at every natural period, for that one, this is a closed invariant curve. And it has some kind of foliations attached to it, which are these kind of stable things. I take the points that, if taken stroboscopically, go to this phase phi. So what is happening with the perturbation is that if I'm at a phase psi and I make a perturbation, then the return will be here. And this difference, psi minus psi prime, will be this phase shift that we had here. So our mathematical model is explaining us what is this phase shift and this return. And also it's telling us more because it's telling us that if we have a locally asymptotically stable limit cycle, if we make weak periodic perturbations, then we have an invariant torus. And the dynamics on this invariant torus is captured by an orientation-preserving circle map, which was the same thing that we had obtained based on the experiments. And this tells us more because the asymptotic dynamics of this kind of map is entirely characterized by a rotation number, which when it's periodic, we get the phase locking in general, and if it's irrational, we get the quasi-periodic ones. So we get everything regarding what we wanted. We get more than that, than what we had observed before, because we know that it's not what we observed did not depend on the particular neuron that we had selected. Those experiments were done on crayfish stretch receptor neurons. But what this mathematics tells us is that this is general. We can do it with locomotion. This is actually experiments that we do. We have people walking, and then we pull on their ankle, and then they stumble, and then they go back. And we can do exactly the same experiments. We do it also on breathing, on the cardiac pacemaker, and all of them will have the same type of behavior. And the mathematics tells us even more. It tells us that the organization of these phase locking and the quasi-periodic regimes follow this Arnold tongue structure. If I put the frequency and the amplitude, I get tongues like this where I have the phase locking, and I get the quasi-periodic ones in between. And if I take the cross-section like this at a fixed amplitude, this explains why we had the sequence of those paradoxical segments in the paper of Perkel. So what happened after this? This was 1964. You see, it was early compared to the mathematics of this. Arnold's paper is 1961, at least the English translation. So what happened is that it took many years for these ideas to sink into biology. And it occurred that in Japan, a mathematician in the name of Yamaguchi did a lot of work in the 70s to spread the ideas about chaos theory and dynamical systems to the broad public. And a young mathematician, Aihara, read those papers and he was influenced. And he went to the lab of a biologist, Matsumoto, and he told him, look, if we take a neuron, it should behave like a dynamical system. And this paper appeared in 1984, but the work was done in the late 70s. So, and he said, let's take the theoretical predictions. So this time the beginning is the theoretical prediction, and let's see if we can reproduce them experimentally. So far it was the reverse, experiments and trying to explain. Here we start with the math part. So do we get phase locking? This is an example of data that they had. So this is the input and the above. Input, output, and this is phase locking. Okay, so they observed phase locking, but this one had been observed before them. They observed other forms of phase locking. They also observed quasi-periodic regimes. So this is a case of quasi-periodic regime. How do we know about it? It's because if we construct some kind of return map, it's going to be constructing some kind of closed curve like this. So this is quasi-periodicity. So the two main behavior. And also, they said that by tuning appropriately the parameters, the amplitude, we should be able to get chaos. And this is what they observed. This is some kind of chaotic pattern that is happening in the neuron. Now, what does it tell us in terms of the neuronal code? We have to think also. But we'll get to that later. So this is what they did. They said, OK, we know that these three types of behavior should occur, and only these, and this is what we observe. And another group, the group of Hayashi, this is this other paper, it's about the same time. They said, OK, do we get this organization in Arnold tongues? Because this was the second prediction. And they did this on a different preparation. And these are all experimental data. So we see that for low amplitude, this is frequency, this is amplitude. For low amplitude, there is some kind of Arnold tongue structure. And the phase lockings are here, and there are some quasi-periodic in between. So the theoretical predictions were confirmed experimentally. And this is where we get in the early 80s. So what does it say? It said that we isolated the neuron, and we looked at how it's behaving for some classes of stimuli. We started from the experiments. We saw that a good theoretical model was some kind of limit cycle, at least when the neuron was pacemaker. And we could get some mathematical predictions based on this, that phase locking, quasi-periodicity, and chaos should occur in some kind of organization in Arnold tongue. And then there was the return to the experiments that validated this. So I could actually stop here, because this is a loop that is complete. It showed us that the neuron is behaving like a nonlinear dynamical system. And it changed a lot of things. For instance, I show you another example. So far I have used periodic forcing. For constant forcing, I showed you just pacemaker firing from the neuron. So here, this is on another neuron. It's always the work of Hayashi. And this is what this neuron is doing if I'm changing only the constant amplitude. So here I have written the amplitudes. You see, this neuron makes this pacemaker firing for this amplitude, but it makes this firing in doublets, quadruplets, this aperiodic firing, and firing in triplets if we are changing only the amplitude. Constant amplitude is being changed. So it's really some kind of nonlinear dynamical system. And if we make a model for it, the model shows us this kind of period doubling bifurcation to chaos. But the previous figure was experimental, purely experimental. This is from a model, but the previous one was experimental. So, okay, we have gotten this, and it even led us to change our view about the working of the neuron. But what is missing here? What we are interested in is the working of the brain. We know the neuron is a nonlinear dynamical system, but what does it tell us about the brain? How does the brain use this? So this is what we want to get. So we want to know what is brain function, how is this being used in brain function, and also, of course, when you're doing biology, there is always lingering in the back of the mind, can we use this in a medical application? So these are the two aspects that I'm going to show next. So let's do some thought experiment. If I ask you to close your eyes, okay, and somebody, for instance, just this sound that you heard, beep, if there is this sound somewhere in the room, and I ask you, try to locate the origin of this sound, okay? How is it going to happen? You are closing your eyes, there is no other clue. How can we locate it? How do we proceed in order to locate the origin of the sound? And there is one animal that does this very nicely. It's the owl. The owl has to catch its prey in complete darkness based on just sound, the origin of sound. How do we do? There is some source of sound coming somewhere, and if it's here, it reaches this ear sooner than this one. It goes through the cochlea. The cochlea makes some kind of Fourier analysis. It takes the different frequencies, and then these frequencies are sent to the neurons. So let's look at this lower part schematically. How it's going to happen is this. This is being sent and this is being sent. Now, why this is a surprising phenomenon? Because the neuron has a precision of millisecond, roughly. The firing of the neuron has a precision of millisecond. Imagine that the sound is traveling a little bit slowly, so 300 meters per second. Imagine that my head is pretty big, 30 centimeters between the two ears. So it takes 1 millisecond for sound to go from this way to this way. So it means that if the source of sound is somewhere here, my brain has to be able to compute something smaller than a millisecond with components that are, whose precision is order of millisecond. For the barn owl, the precision has to be microsecond. So 1,000 times better than the precision of the neurons that are being used. How this is achieved is thanks to phase locking. Because if the neurons phase lock, then even though they are not very precise themselves, thanks to phase locking, they become very precise. And this has been used by engineers for many, many years to obtain very reliable oscillators. So this is being used also in the brain. So if I have this one, because it started sooner than this one, I have some delta t here. So this delta t will be preserved between these. And then I have specialized neurons. These specialized neurons can tell the difference between short times of firings between these two. So phase locking has this functional application. It allows, this is what the mechanism I showed is for the bird auditory system. It's not for us. So for the owl, it works like this. And it allows this very big precision in the working. So this was one example of functional significance of these dynamics that we saw. How about the medical application? Epileptic seizure is some kind of storm in the brain. Okay? It means that some neurons suddenly start to fire in a very erratic way, but synchronously. So it's some kind of big storm. And just like we like to predict storms that occur in outside of the brain by meteorological methods, then we like to be able to predict when epileptic seizures are going to occur. But for outside, we have Navier-Stokes equations and things like that, and we can do all kinds of modeling and try to monitor and go on. The brain is far too complicated. We don't have equations like that to make the models. But if we know that this is a dynamical system, then the onset of epilepsy corresponds to a change in the dynamics of this. So what we are going to do is we are saying we have a dynamical system. We estimate somehow its phase portrait by appropriate methods directly based on the data. And when we see a qualitative change detected by some quantifying indicator, then we know that we are changing the dynamics, and this is the onset of epilepsy. And with this method that has been applied by this group to detect epilepsy, they could detect the onset of epilepsy minutes before it arrived, whereas linear methods could do it only a few seconds or half a minute before. So there was a huge improvement. And this was published in Nature Medicine in '98. So Nature Medicine is for medical doctors. It's not for mathematicians. It's not for physicists. This is for doctors. And even later on, they got another paper in the Lancet on the same topic. So the Lancet is, so anticipation of epileptic seizures from standard EEG, the work of Michel Le Bancuyen. And this is in the Lancet. The Lancet is a very standard medical journal that most practitioners read. Okay, so this is really for medical doctors and for the applications. Okay, so what I have shown so far is that there was some kind of bad guy, which was linearity, and the good guy, which was nonlinearity, and there were, over many years, there was some kind of fight between them. And nonlinearity was at first held on the side for many years. People believed that it was not occurring. And then progressively, it won battle after battle after battle. And then it had its way to mainstream. And now you see people are working on these topics in medical applications. So we saw the functional significance, we showed the medical application, and now I'm going to talk about a different system. And this is the motor cortex. So motor cortex is somewhere here, and it's dealing with the control of movement. This is the part that tells, okay, move your hand like this, move your hand like this. This is the part that is giving these orders. It's sitting here, so you see the motor arc is something pretty complicated. It has visual parts, sensory parts. It has motivational system, but we are dealing with this last part that is giving the order to the spinal cord and then to muscle and hands. So this is really the last step. We are dealing with this last step. And we are going to read the code at this stage. So just to put things how they are located, this is the motor cortex is somewhere here. This is the cerebellum. If there is time at the end, I will say a few words about this one too. But for now, we concentrate on this one. So how is this working? So as I said, here, it's really these neurons that are giving this one before last order before the muscles. Okay? We want to deal with these neurons. And, okay, this transparency doesn't look good. But there were a series of 4 papers in Science. 3 of them made the cover of Science. Our librarian didn't want me to take these journals out of the library to make nice copies. So this is why they look like this. But anyway, they made the cover of Science. There were 4 papers by the group of Georgopoulos who characterized this neurons. What they did is a very simple experiment. They had monkeys sitting and holding their hand at a fixed position. And then the monkey had to move to 8 directions, the hand. So there were signals, move this, move this, move this, in all these different directions. And at the same time, they were recording neurons from the motor cortex. And they were looking at how these neurons respond to movement in different directions. And they observed the following thing, is that neurons in the motor cortex, not all of them, but some of them, have a preferred direction. There are neurons, if I do this, some of the neurons in my brain have this is their preferred direction. It means that their firing rate is maximal when I'm doing this. If I move this direction, their firing rate will be lower. They will be still firing, but with a lower rate. If I take another population of neurons, for them, this movement, this direction will be the preferred direction. They will have their maximal firing rate in this direction and lower firing rates in the others. And what they realized is that if we represent the vector in three-dimensional space of the preferred direction, and we take any other direction, then the rate is given by something like this, by cosine of this. So if I take 2 directions in space, okay, I take the cosine between these two. If this was the preferred direction, I get the firing rate for that one. This is what the data looks like, okay? It says these neurons have this kind of tuning. What they realized is that, okay, if I'm looking at these neurons, I cannot tell where the motion is because each one has some kind of broad tuning curve. It's not doing it precisely. But what they realized is that if we take the preferred direction of the neuron, if we are looking at many neurons simultaneously, we have a population code. Each neuron has its preferred direction. And we put a weight here, and this weight is the rate of firing of the neuron from which we have subtracted some constant. So basically the rate of firing of the neuron. Then we obtain a vector, d. And what they observed is that this vector d corresponds to the direction of actual movement. So this quantity is estimated directly from the brain, and then it's compared to the experiment, and it matches. So this is called a population coding. So what the experimental data looks like is this. So let's not look at all the details, but this arrow represents the actual direction of, let's take this one. This arrow represents the actual direction of movement, and this one, the one predicted directly from recording from the brain. So the fit is not too bad, you see. In general, the two are very close one to another. And we can attribute this because we are using a finite sample, there's variability, and so on. But directly from recording from the motor cortex, we can see what this hand is going to do. And they did even more with these monkeys. They taught the monkey that it would wait 1 to 3 seconds before doing the movement. So the monkey was supposed to move the hand from here to here, and then but it learned that, okay, it has to wait 1, 2, 3, and then do it. And what they realized is that in those 3 seconds, they could already predict the direction of movement before the monkey was doing this. And what I didn't say is that so far all that I have said is about nonlinearity. Okay? Nonlinearity is wonderful, but look at this. This is purely linear. So when we are going back to the brain, it became linear. So what can be done with this linear thing is a lot, actually. And this is the series of experiments by the group of Mikolailis. And this is when I say about reading the brain. In these experiments, so this is experiments by the group of Mikolailis. Oops. Okay. So letters to nature. You see the monkey is sitting here and it's performing some task with its hand. Okay? And what this experiment shows is that just with the mind, with the brain of the monkey, we can control a robot. So usually what we do is we can put sensors here, 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 and the muscles, and we can connect this to the robot, and I do this, and the robot does the same thing. It's getting directly the information from what I'm doing. But this is not this experiment. In this experiment, the recording is done from the brain, and then the data from the brain is sent to the robot. So the robot receives the same thing as the nervous system. And what you see is that there is a very good matching between the movement of the hand of the monkey. It's recorded in the brain based on that principle that we know about directions and things like that. And the robot, which is not directly connected to the monkey except to its brain, the motion is going to be the same. And what they did is actually they put a robot in MIT and they did the experiments in Duke, and they sent the data by internet. And they still got a good matching between the two. And they did the same experiments with rats, and this time the rats learned to activate something without, in this case, the monkey is doing the same thing. Okay? But for the rats, after some time, the rat learned merely by doing the activation, by thinking. So the rat was supposed to apply its paw on some level and get something. After a time, it learned that it didn't need. It just thought about pushing the hand, and the hand went down. So this is how far we have gotten in reading the mind. And this is something. And so I said all of this talk was about, okay, starting from linearity, single neuron. The single neuron is such a nonlinear thing. It's wonderful, dynamical systems. We can do all the predictions, get confirmation from the experiments. But at the single neuron level, we have this nonlinearity. But when we are moving to this area of the cortex, we get something that is very linear. So we have some ideas about that, but that will be for another talk. So I will stop here. You mean long-term depression or spreading? There are many works on epilepsy. I think that this is a... You mean from the theoretical side, from the experimental, what about?
About the connection between this theory and an explanation of spread depression.
I think that would require some detailed talk outside of this. Okay, of course, it's a good question. Is epileptic crisis related to some kind of dynamics? But I limited to single neurons activities. That one requires, of course, what is happening in a population and the interaction with many systems and changes. So it's more complex than what I have been explaining. This one. It's just fun. I think it says that Gauss's brain was much more convoluted than a German worker. So we are still a long way from understanding how Gauss's brain was working. But this is to show that, okay, this could be our goal, to understand how Gauss's brain was working. I think quite a few people here would be interested in that. So one final remark. I selected some examples from the literature. There are many, many more. And I tried to select these examples because the talk was here in Brazil. So the talk that I showed about the seesaw response was performed by José Pedro Segundo, who is from Uruguay. The work was done in UCLA, but he's from Uruguay. The work that was on epilepsy, it was designed by Francisco Varela, who is from Chile. He worked in France, but he was from Chile. This work on the monkey and the movement of the monkey is done by Miguel Nicolelis, who is Brazilian. He works in Duke, but is Brazilian. And another work about the cerebellum that I didn't say, it's about learning in the cerebellum. That one was by Rudolfo Linas, who is in New York, but also he's from Latin America. There is also a very strong group of Latin Americans working in neurosciences. Okay.
little bit heard about the spread in depression phenomenon.
So you work in this topic, or you're just?
No. I'm just interested because, well, my